Hello friends, Namaste and Jai Hind. Welcome to my show Technology and Engineering Made Simple. In this session, we are going to study an important mathematical model called derivative. It is also a mathematical operator, that is, it operates on functions and signal and generate the output. So we'll see various interpretation of derivative and then various applications of in electrical engineering, signal processing and artificial intelligence. The simple definition of derivative for a function x of t is defined as dx by dt, which is nothing but change in x with respect to time t. Another interpretation of derivative is a slope of a function. Slope of a function can be described graphically as shown in the following figure. Consider a function x of t varying with the time t in a red color graph. Now consider a point P at which we want to determine a slope. So standard procedure is draw a tangent at point P and then measure the infinitesimal small distance dx and dt in the direction of x and t. And then one can calculate the ratio dx by dt, which is nothing but the derivative of x with respect to time, and that will give the slope of a function. Now, what is a exact application or what information one can find out from the slope? Now here we'll consider two important points. One is a minima and second one is a maxima, and then we'll compute the slope at each point. Now the consider point Q, which is a minimum of a function, and at this point the slope of tangent is 0. Similarly, we can see the point R at maxima, and then again the slope of tangent is 0. This idea is used in the optimization theory, where many electrical, non-electrical systems can be designed with optimum cost function. That is, that cost function is either minimized or maximized, and hence it plays a very vital role in the theory of optimization. Now, here there is one dilemma. When the slope is 0, it can be either minima or a maxima. So how one can find out whether function is minimum or a maximum? So there is a simple procedure, that is find out a second order derivative. But before that, we'll try to understand this graphically. Now consider 2 points before and after Q, which is shown by two tangents before and after Q in the green color dotted lines. When you see the slope of a point on the left hand side of Q, one can see the line is going or climbing in the negative direction, and hence the slope is negative. Similarly, if you see the dotted green color line on the right hand side of point Q, then line is climbing in the positive direction. So here, when you approach point Q from left to right, the slope is negative, then it becomes 0, and then it becomes positive. So you approaches from negative slope to positive slope, and hence the slope of the slope, which is nothing but the second order derivative, becomes positive. So here, whenever second order derivative is positive, the point is minima. Similarly, we can apply the same concept by computing slope before and after the maximum point. And here one can see the slope of a tangent on the left hand side of R is positive, then it becomes 0 at point R, and then slope becomes negative. So at maxima point here, the second order derivative becomes less than 0 because slope finally becomes negative. That is, a slope of a slope becomes negative, which is nothing but second order derivative becomes less than 0. And these are the ideas used in the optimization theory subjects. Now we'll see another interpretation of dx by dt, which is a force. Basically, the change is nothing but the force according to Newton's second law, which is nothing but rate of change of momentum is directly proportional to the applied force. So momentum is given by mass into velocity, and therefore the force is equal to rate of change of momentum with respect to time. And then equation becomes force is equal to mass into dv by dt, where v is a velocity. dv by dt is equal to force divided by mass. So the mass is a constant, and therefore the change or a derivative also represent a force. Now we'll see the one more interpretation of derivative as a system, which is typically used in synthesis of the system. So here in electrical engineering, one can find there is an electrical device called a capacitor, which stores the charge per unit voltage, and therefore capacitor is defined as Q by V. Now Q is equal to CV. This is a total charge stored on the capacitor for a voltage V. Now, what is the current? It is a rate of change of charge, and therefore current through a capacitor is given by I is equal to C into dV by dt, and therefore dV by dt is equal to I by C. So one can say the derivative represents a capacitive system. Similarly, if you apply Faraday's law of electromagnetic induction, one can see the voltage V is equal to L into di by dt, and therefore di by dt is equal to V by L. So it represents inductive system. Now there is a one more interpretation of derivative which we call a system representation. Consider a simple function x of t is equal to cos of omega t, which is nothing but the cosine wave or a sine wave or an oscillator. So if you differentiate with respect to t, you'll get minus omega into sine of omega t. And when you calculate second order derivative, it will come minus omega square into cos of omega t, and cos of omega t is x of t. If you substitute that, then you will get a simple differential equation d2x by dt square plus omega square x equal to 0. Now this represents the oscillator system because the solution of this equation is nothing but x of t is equal to cos of omega t. When the previous three equations are not given, then it is very difficult to understand what does this differential equation system represents. So obviously it is a system, but what is the exact output of this system? And that is nothing but the solution. Once you find a solution of this equation, you'll get x of t is equal to cos of omega t. So one can represent this as a system with the output yt is equal to cos of omega t. Then input applied to the system is x of t. There is a one more interpretation. The derivative of a constant is 0 and it increases as input start changing. So derivative is low when input is slowly varying, and derivative becomes high whenever it is varying rapidly with respect to time. And therefore, basically, it allows high frequency to pass through it while it rejects low frequency. For low frequency, either output is low or it is 0. For example, the constant, which has a 0 frequency. Now, there is a one more representation of derivative in the form of a vector differential operator, which is also called del operator. Basically, it is the same as derivative. Only thing is various components. In this case, 3 components represents derivative in each direction x, y and z. That is a dabba by dabba x, dabba by dabba y and dabba by dabba z. We'll see the first principle of derivative or definition of a derivative. Dx by dt is equal to limit h tends to 0 x of t plus h minus x of t divided by h. So similar definition can be obtained by replacing t plus h by t. So the modified equation becomes limit h tends to 0 x of t minus h divided by h. So one can use one of the definition of say type 1 or type 2 to compute the derivative of a function. Now we'll apply this in a discretization of a differential equation. For example, consider a function x of t which is sampled using train of impulses, and we generate xn. Now t is equal to nts, so x of t will become x of nts, and which is equivalent to x of n because the ts is constant, and one can normalize that value to 1. So your h becomes ts, that is equal to 1. Now if you substitute these values in type 2 definition of derivative, then dx by dt, which is nothing but y of t, will become y of n equal to x of n minus x of n minus 1. Now h is equal to 1. I know we have not studied z transform yet, but just for the sake of clarity, if you compute z transform on the both sides, you'll get equation y of z is equal to x of z minus z inverse into x of z. One can find out a transfer function of a system y of z divided by x of z, which is h of z equal to 1 minus z inverse. Even if you don't understand this equation at this point of time, don't worry about it. Now I'll see another operator called a Laplacian operator, which represents second order derivative in x and y direction. It has a tremendous application in image processing. So this is basically a del operator with a second order derivative in 2-dimension space. When you apply discretization to this Laplacian operator, you will get a very important matrix function which acts as a transfer function of a high pass filter as shown below. Now here, consider second order derivative of x with respect to time, which can be computed as a derivative of first order derivative. So g of t is a first order derivative of x of t. You can substitute the first principal equation for dx by dt and then apply it to the second order derivative. Now in second order derivative, use type 2 definition of first principle, and then you can achieve the final equation as limit h tends to 0 x of t plus h minus x of t plus x of t minus h divided by h square. And when you discretize this, that is replacing t by n and h by 1. Then we'll get another equation, y of n is equal to x of n plus 1 minus 2 into x of n plus x of n minus 1. This is a equation applied in horizontal direction. If you apply this equation in vertical direction as well, that is because we are computing second order derivative in both x and y direction. When you superimpose on each other, you will get a nice matrix function h of xy is equal to 0 1 0 1 minus 4 1 and 0 1 0 1 minus 4 1. It is a difference equation explained in the previous step, that is a yn is equal to 1 into x of n plus 1 minus 2 into x of n plus x into n minus 1, and same equation is organized in a vertical direction. So minus 2 will become 4, and here you will get a two-dimension matrix equation as a Laplacian operator. Now here we can verify this operator as a high-pass filter using simple MATLAB simulation. Now here we can see the MATLAB simulation with a simple code. So same filter is implemented in MATLAB as h is equal to this 3 by 3 equation. Then we are reading the image and then we are filtering the image I using filter H, and then we'll see output whether it is really giving edge detection or high pass filtering or not. So when we run this, you can see the output here, where the left hand side image is the original image while the right hand side image shows edge detection. Edges are nothing but the high pass signal in your image, while the low pass signal, where signal is not changing rapidly or it is almost constant, the output is 0, which is shown by the blackish area, while edges are detected by the white or bright spots. So it acts as an edge detection filter. I hope you must have liked this lecture, and thank you for watching my show.